Hello, Barbara. Can you hear me?
Yes, I can. Hi,
Okay,
Ellie.
just
Hi.
checking. Hello. Can you put this live to the beginning?
I can.
Thanks so much.
Thank you for reminding me.
Hmm? No problem. So we have, I think, two people already with us. Good afternoon. Let's just wait a few minutes for our attendees. Good afternoon, everyone. Let's just wait a few minutes before we start. It's almost 2 o'clock, but we'll give a few minutes to allow other participants to join. So Barbara, we're gonna give a few minutes more, and then I will start the presentation. Probably around 2:03, 2:05, I will start. Okay?
Sounds good.
All right, I think I'm about to prepare to start. Just want to let everyone know that once I start, I'm going to be recording the presentation. Just please keep your cameras off and microphones too. Thank you. My microphone is off. Apologize for that. Welcome, everyone. Thank you for joining us today to another pollution prevention webinar session. The topic for today is autoclave design, a simple choice as substantial climate connection. My name is Marley Carmona. I am an environmental specialist focused on pollution prevention. I work for the Center of Sustainable Energy and Environmental Engineering here at East Carolina University, and today I'm going to be the moderator for the session. Our guest speaker is Barbara Wells. She is from Priorclave, and she will be bringing insights on autoclave design and how these choices can influence and help us reducing energy consumption, lowering water usage, and minimizing carbon dioxide emissions. So with that said, let's start. Please, next. Let's move to the next slide. The mission of our center is to promote, enhance, and serve. We do this by providing scholarly applied research. We also provide consultancy for sustainable energy development and conservation of natural resources. The center also strives to enhance public awareness and promote renewable energy technologies, focusing specifically on research and workforce training. Next, please. Thanks to multiple grants, our center is able to offer a variety of services, specifically to manufacturing facilities. Some of our great offerings include energy, water, and lean assessments. These are completely free, and it provides technical assistance to address issues like energy in water, minimizing waste, and we provide tailored recommendations on you providing a private report, so we don't share this information with anyone other than the people involved in the company. Besides that, we also have different services such as regional and energy training, regional workshops, technical and engineering support, cash flow and market analysis, and return on investments. Next, please. And just a reminder, as I said in the beginning, we are recording this session and the presentation slides will be available at the end. So be in the lookout for that email. And also, please feel free to ask questions. We typically have a Q&A session at the end. But I understand Barbara will be happy to receive your questions. If you need to interrupt her, that is fine. She would love the interaction, so please feel free to do that. And also, we are happy to receive your feedback so we can do better for the next session. Next, please. So yeah, that's that. And now we'd love to welcome our speaker, Barbara Wells. She's the president and CEO of Priorclave North America. She is currently leading operations in US, Canada, Mexico, and the Caribbean for UK-based Priorclave. She's also working in Autoclave market, specifically in the segment into jacketed and non-jacketed products. She's a big advocate for jacketless autoclaves in North America because they produce significant environmental benefits, which she's going to talk about more today about that. So without further ado, I'm going to turn it over to you, Barbara, so you can continue the presentation. Thank you.
Thank you, Marley. What a
You're
kind
welcome.
introduction. That was great. I think you did part of the presentation already, too. Thank you. I'm actually thrilled to be here because this is one of my favorite topics. There's a connection between laboratories and climate goals, and that is what we're going to talk about here today. I'll also dig into autoclave design and share lots of plug load and water usage data. And before I'm finished, I'll highlight additional resources and still leave time for questions. I'm not an expert in construction or in utilities, so I really hope the questions are about autoclaves. And I hope that you put a bunch of them in the chat. And better yet, as Marley said, please interrupt me. I tend to get all fired up on this topic and I can talk too fast, trying to go really slow, but your interruptions would be most welcome. Overall, I'm here today because I share ECU's commitment to sustainability. As CEO of an autoclave company, I'm approaching the topic from a corporate perspective, but my passion is not laboratory equipment. My passion is reducing the environmental impact of research. Over the years in this business, I've learned that it takes staggering amounts of water and energy to do research. And I've also discovered that labs and lab equipment are everywhere. Sure, we expect to see them in hospitals and schools, pharmaceutical companies, but they are also in manufacturing, agriculture, food production, airports, and even in museums. So for the purposes of this presentation, when I say labs, I'm talking about all types of research environments. The sheer number of labs adds up, but you might wonder how significant they really are for overall sustainability goals. We can look at US labs in the context of 6 million industrial, commercial, and institutional buildings, which contribute a big chunk of water and carbon emissions in America. Within the ICI sector, there are about 153,000 laboratories. So labs only make up about 2.5% of these buildings. Why would this small percentage matter? Well, it's what happens inside those labs. They have specific protocols and equipment, so labs need things like strict temperature and humidity control, which means higher HVAC usage. Also, they use specialized tools like fume hoods and, of course, autoclaves that are energy intensive. All this results in the numbers you see here on this slide, which are based on a comparison of consumption by square footage. Some specialty labs, like clean rooms, can use up to 100 times more energy than a similarly sized ICI building. When it comes to water, high laboratory consumption is largely due to the need for washing and rinsing equipment, cooling systems, RO water systems, and steam generation. A 2022 report from the Royal Society of Chemists found that 60% of total campus water consumption came from labs, not from dorms, cafeterias, sanitary maintenance, nothing like that, all laboratories. At UC Berkeley, where they've been working on this problem for decades, that figure is still close to 20%. Now, if just half of all American labs were to reduce their energy use by 30%, the US EPA estimates we could save 84 trillion BTUs of energy every year and cut carbon emissions by 19 million tons. So I think I might have missed a slide. Hold on, too excited. Okay, so now we know traditional lab practices come with some unintended environmental consequences. It makes sense to check out the role of laboratory equipment in both energy and water use. And you know where this is going. Autoclaves typically use more water in the lab than any other equipment. There's somewhere between 160,000 and 320,000 autoclaves in America. For anyone who's not familiar, autoclaves use temperature, steam, and pressure to sterilize whatever you put in the chamber. It's like a big Instapot. They're crucial for neutralizing microorganisms, spores, and viruses, but they serve other purposes too, like quality assurance, curing materials, and durability testing. Why do they use so much water? Autoclaves use water for three things. First, to generate steam, obviously. Second, they use water for effluent cooling. When a typical autoclave is in use or idle, steam is condensing inside it, and that condensate must be cooled before it can drain. Third, autoclaves use water to create a vacuum. Water serves as the operating fluid in a liquid ring pump or a Venturi ejector pump that's used to run vacuum cycles. Typical autoclaves come standard with vacuum features because they're required in hospitals and other high throughput settings. But not all laboratory loads even need a vacuum cycle. Many labs never run one. In any case, extra water runs down the drain at the end of every vacuum cycle. And now for a point of clarification, there are small benchtop autoclaves used in healthcare, veterinary clinics, and hopefully in body art studios, but these don't use excessive water or energy. Today, we're focusing on standalone autoclaves that are 100 liters or greater. Now we can dive into autoclave design. Woo! We know why autoclaves use water, so let's look at how they get it. There are three ways. They can be fed by house steam, they can use an external steam generator, or have an integral steam generator built in. Typically, the water must be RO, DI, or softened, and sometimes that water needs to be heated or chilled before it even reaches the autoclave. So it starts to make sense why so much water is going into autoclaves. This slide shows a typical jacketed autoclave. The sterilization chamber is double walled, and the middle picture shows that there's a small space called a steam jacket between the walls. As you can see in this diagram, steam is piped into the chamber from an external source. In this case, the inside view on the right shows what's referred to as an integral steam generator. It's called integral because it's located inside the autoclave, inside the cabinetry, maybe underneath the chamber, but it's not integral to that machine. It requires its own power source and its own water feed. When an autoclave is on or in standby mode, the jacket fills with steam to maintain a steady temperature all the time. Ta-da! But here's the clincher. Most autoclaves are designed to be on or in standby mode all the time. They're always hot and ready, so they're always drawing water and electricity. It's a lot of water. These figures are pretty typical of jacketed autoclaves based on the published specs of major manufacturers. They assume that researchers are using their autoclaves for 3 vacuum cycles per day. Why 3? I chose this number because a 2014 study from the Center for Energy Efficient Laboratories found that 3 hours a day is the most common use case for university labs, and because this figure matches the profile of our laboratory customers across all industries. So what does this mean? For a typical jacketed autoclave running a vacuum cycle, the RO water use is about 80 gallons. So multiply it by 3 cycles, and we've got that 240 gallons. Now, for every gallon of RO water produced, there's typically 5 gallons or more of reject water. That means those 240 gallons produce 1,200 gallons of reject water that you have to treat before you can dispose of it or reuse it in any way. But wait, there's more. Jacketed autoclaves continue to vent clean water even when they're idle. Across manufacturers, a typical rate is 5 gallons per hour. If we run that over a day, that gets you the 120 gallon figure. All of this translates to a cost of about $5,600 per autoclave per year, based on the average cost of water here in America. But who cares about the money? We need to save that clean water. There are some recent studies that show that water usage of jacketed autoclaves is even more dire. A 2016 study from the University of California, Riverside found that each of their autoclaves was using over 600 gallons of fresh water per day. Oh, and this is regardless of whether the autoclaves were in use. And it doesn't even account for the RO reject water that was needed to feed them in the first place. This study also measured the effluent cooling water, which isn't typically part of the water required to run an autoclave cycle. So manufacturers, we don't have to report that. Remember, effluent cooling, also known as tempering or bleed water, is needed to cool the steam that's always condensing inside the jacket before it can go down the drain. Many older models use effluent cooling water continuously. For example, Stanford did an audit of their autoclaves in 2017, and they found they were using an average of 1,550 gallons of water per day each. Again, whether or not they were idle. Most recently, there's been a new study from the University of Alabama at Birmingham that tracked 50 gallons of fresh water down the drain with every cycle, not counting any reject water or effluent cooling. It's super common for labs to have a mix of autoclave models, some that are 25 years old or older, and others that are brand new. Oh, and many research campuses have over 100 of these things. Altogether, these systems waste more than 10 billion gallons of fresh water every year. I'm going to show a short clip. Bottom right corner.
How many gallons a day do you suppose that is?
Oh, that's a fair amount.
And this unit hasn't been working for how long?
That's really bad.
Since the last, okay, so since the beginning of last month. Beautiful.
Well, that wasn't really beautiful. It's a crying shame. Shifting to plug load, please bear with me while I walk us through these numbers using my notes. This overall figure reflects the electricity needed to run the integral steam generator and an air compressor, which commonly is required for operating the doors, seals, and actuators in a jacketed autoclave. It doesn't include the energy needed for the purified, heated, or chilled water that they often require, or the extra electricity to run the operating system itself. Just like we did with the water, this estimate assumes the autoclave is running for 3 hours or 3 cycles per day. It factors in a 27 kilowatt steam generator and a 5 horsepower air compressor running for about 3.5 hours, plus standby power. Here's how the math breaks down. 3 operational hours of steam generation adds up to 81 kilowatt hours per day. The air compressor running for about 3.5 hours gives us the 13 kilowatt hour figure, and an autoclave with an integral steam generator typically uses about 200 watts on standby. So if we multiply that 0.2 kilowatts by 21 hours, that adds 4.2 kilowatt hours per day. To put this in some context, the University of California, Santa Cruz reported that their lab buildings accounted for just 1/5 of the campus's total square footage. But the labs consume 1/3 of the electricity for the whole campus. Jacketed autoclaves contribute to a significant draw of power by laboratories. If energy expense is a concern, it costs roughly $4,600 a year to run each autoclave based on average electricity rates. It adds up. Once again, we see third-party research that illustrates a wasteful picture. That same University of California Riverside study shows an annual energy use of about 1.1 gigawatts per autoclave. And that energy audit at Stanford, that called out their 167 autoclaves for using as much energy as nearly 20,000 computer monitors. Meanwhile, at Virginia Tech, they discovered that each of their autoclaves was using an average of 60 kilowatt hours per day. And we know that those autoclaves aren't in use all the time. Finally, just a couple of years ago in 2022, numbers from researchers at Penn State showed that each of their autoclaves uses as much energy as 3 US homes every day. The good news, the National Renewable Energy Laboratory says that a drop in energy use of 30% at laboratories would be like taking 1.3 million cars off the road. So laboratories and their special equipment can make a real difference to overall climate goals. It's studies like these that have helped push manufacturers of steam-jacketed autoclaves to rethink water and energy use. Many now offer water-saving add-ons that fit inside the autoclave or install nearby, like the ones shown here. But here's the catch. These water-saving add-ons need a power source, and some require chilled feed water. So for an extra equipment investment, you can save water, but it'll cost electricity. And that's what happened at Virginia Tech when they were looking for a new autoclave in 2019. They wanted to purchase the optional Steri-Green system, but they found it would require the lab to be remodeled to provide the right electrical power, and it would require more space, maintenance, and heat load than they were prepared to deal with. So they bought a jacketed autoclave without water-saving features. Heartbreaking. There are recommendations for how to make existing autoclaves more efficient. At UC Santa Cruz, they allocated $374,000 to water-saving projects, including an autoclave retrofit program. They added recirculating systems to 7 of their sterilizers and reduced water consumption from 1,500 gallons to 20 gallons per autoclave per day. What we don't know is the effect on their energy consumption. There are some non-electric devices that can help. A water miser, for example, can be retrofitted to a jacketed autoclave. It monitors the temperature of the effluent and only adds cold water as needed. It's another expense, but it's worth checking out. If you don't want to worry about add-ons or retrofits, there's an alternative. Hooray! Non-jacketed autoclaves have been available in North America for about a decade. People are just learning about them, and they're not right for every situation. For high throughput or terminal sterilization, like what you'd find in hospitals or pharmaceutical production, you still need a jacketed autoclave. But jacketless autoclaves are ideal for sterilizing lab items, like glassware, media waste, fermenters. They're also efficient for tissue culture, substrates, sealed containers, and even destruction testing. Let's take a look. Here's a happy scientist who's packed his non-jacketed autoclave with typical lab items. You know why he's happy? He's happy because he knows he's saving water and energy. The less water and less energy figures on this slide are from that UC Riverside study that I've been referencing. The comparison was between autoclaves with comparable size and features. The best part is that there are no extra water or energy saving features needed. These autoclaves are sustainable by design, thanks to the simple way they make steam. If a jacketless autoclave is the right fit for a lab, obviously making a change can go a long way toward meeting sustainability goals. And it is great to be here today to help get that word out. Let's have a look at how non-jacketed autoclaves make steam. Here we can see a jacketed unit on the left next to the non-jacketed model on the right. There are some obvious differences. You can see that the jacketed one has a rectangular chamber and a power door. It also has an inflatable seal. That's why they need an air compressor. The jacketless one on the right has a round chamber and a manual door with the simple pressure gasket. But the most important difference is how they make steam. You can see the integral steam generator on the left sitting under that chamber, and it's ready to pipe steam up into the jacket. And you can see some electric heating elements in the bottom of the chamber on the right. The non-jacketed autoclave is on demand. So when it's time to run a cycle, you have to turn it on. There is no standby mode. Water fills the bottom of the chamber just enough to cover those heating elements, and voila, steam on demand. A difference that you can't see here is that the jacketed unit probably requires RO water. There's a lot of infrastructure and maintenance to keep it up and running. The jacketless model runs on soft tap water. As I mentioned earlier, many jacketed sterilizers are designed to run on house steam. This not only adds complexity, it also adds to the carbon footprint. Fortunately, there are ways to make steam that don't involve natural gas or coal. More and more organizations are making the switch from steam plants to electrification, especially those focused on reducing their carbon impact, like the University of Alabama at Birmingham. These figures are from their new study, and that 45 pounds of steam needed for one jacketed cycle is roughly equivalent to driving an average American car about 2.5 miles. By contrast, the electric heaters inside the chamber of a jacketless autoclave can be powered by low carbon or no carbon energy sources like wind and solar. This is how replacing jacketed models with jacketless ones can be a key step toward lab sustainability and reducing overall carbon impact. Quick recap. It boils down to autoclave design and steam generation. The submerged heating elements in the jacketless design simply require less water and energy to produce steam. Plus, features like manual doors and valves minimize the utility requirements, which is why there's no compressed air. And the use of tap water means no reject water. The figures shown here are based on the published specs for a 20 by 20 by 38-inch chamber, which is a standard in the autoclave industry, and a comparable 320-liter non-jacketed chamber running a single vacuum cycle. The consumption differences are truly substantial. I promised to highlight some specific resources, and here are 3 amazing organizations. The first one is I2SL. They provide a real community for sustainability people in the life sciences industry, and they host an annual conference that's going on right now. People are sharing trends in lab design, engineering, benchmarking, and decarbonization. They also have a lot of active local chapters with their own resources. The next one is My Green Lab. This is an established nonprofit that enables labs and lab equipment manufacturers to be best in class. One of their main offerings is a Green Lab certification program that focuses on energy use, water conservation, and waste management. There's also a self-certification program. They provide guides and webinars to help labs implement eco-friendly practices. They are highly collaborative in support of bigger climate goals around the world. Finally, we have Lab Renew. This nonprofit takes the elements from I2SL and My Green Lab and brings them into the lab for real-world impact. They will literally come to your lab for free and provide a sustainability assessment and give tailored recommendations for reducing consumption and waste. There are so many good people doing good work in this world. One more resource I wanted to mention is My Green Lab's ACT database. If you've not heard of it, the ACT label is like an Energy Star label, but for lab equipment. Manufacturers go through a rigorous third-party assessment process, and the resulting label is available for researchers and procurement specialists, especially, to help guide purchase decisions for the lab. ACT stands for Accountability, Consistency, and Transparency in Manufacturing. What I love about it is that it encourages manufacturers like my company to create greener options, leading to a more sustainable supply chain overall. It's a win-win for labs and the world. You can find all the manufacturers and labels in the ACT database using that link in the upper left corner, right under the logo. or just go to My Green Lab and look for the ACT label. Back to autoclaves for one last slide. Since jacketless models became available in North America, they've replaced a few hundred jacketed units, which has saved enough water to fill a reservoir the size of Lake Merritt in Oakland, California, and enough electricity to power the average American home for about 1,800 years, and prevented the equivalent of CO2 emissions from 1,700 cars over the course of a year. But don't forget, there are an estimated 160,000 to 320,000 autoclaves in the US. Imagine what would happen if we replaced even 60,000 of them with non-jacketed models. It would be billions of gallons of water and kilowatt hours saved and gigatons of carbon. We're getting there. I hope you got what you were looking for out of this presentation today and found something to cheer about. A simple autoclave choice can help save the planet. Every single large, non-jacketed autoclave sold keeps a jacketed autoclave out of the lab. Please help spread the word, and thank you for coming. I can't believe no one interrupted with any questions at all.
It's okay. Thank you, Barbara, for this insightful presentation. We now are going to have time for questions from the audience. Maybe you can move the slide, please.
I can.
Thanks so much. Here's our time. If anyone in the audience have a question for Barbara, please, you can turn your mic or leave it in the chat. Seems like we have one question already. Let's see. How does the lack of a jacket and jacketless autoclaves affect the consistency of temperature distribution throughout the chamber?
Great question.
Could you help us with that?
I can. So a couple of points there. To begin with, you saw the difference in chamber shape. So traditional jacketed autoclaves are rectangular. They, by design, have cold pockets in the corners because steam circulates. In addition, Mother Nature wants pressure vessels to be round, so the steam circulates beautifully in a round chamber. The heat is produced directly in the chamber, so it is evenly distributed in the chamber with no cold pockets. I want to know if that answered your question because I can go on forever about this. Yeah.
Somebody in the audience says, Vincent says, thank you, Barbara, for the wonderful presentation. Great job.
Thank you, Vincent.
Thank you for the feedback. We welcome that too. Any other question for Barbara?
There must be something.
Well, I think I have. Oh, there is another one there. Are jackless autoclaves approved for use across all industries, or are there specific sectors or regulations that limit their application compared to traditional jacketed autoclaves?
Another great question. Sterilization is sterilization. So in theory, you can use a jacketless autoclave for anything that you would use a jacketed autoclave for. However, in North America, jacketless autoclaves are primarily used for non-medical applications. So we're talking about research laboratories. The reason for that isn't a lack of sterility. It's partly whether or not companies want to get FDA approval. It's also a matter of competing in that space. The primary autoclave companies in North America serve the medical market. So other manufacturers may not wish to be involved in that competition. There are times when, as I mentioned, a jacketed autoclave is required. There are pharmaceutical production instances where they can't have any soft tap water. They need to have highly pure water in order to compound their products properly. I can't really speak much more to that, but you get the idea. Hopefully that answers that question.
Barbara, I have a question. Do you have any case study or success story from manufacturing facilities maybe that have upgraded to the jacketless autoclave?
So far, all of our actual, the only studies that I can find in the field are from university campuses. I have empirical knowledge from my own business, customers who will tell us what's happening when they switch, but no one has conducted any third-party research that I've been able to find. If someone in the audience has a manufacturing facility and would like to set up such a test, we'd be happy to work with you on that.
Thanks, Barbara. We have another question. If CO2 emission saving is excluded, is there a saving of any kind when converting to electric autoclave?
Wow, I don't know. I hadn't even considered that question. I mean, obviously, because jacketless autoclaves are an on-demand system, there's electricity saving because they're not always hot and ready. And they're not always using water, like that short video clip we saw. So those would still be savings separate from the carbon footprint. Another savings that's more subtle is the manufacturing of a jacketed autoclave is far more intense than a jacketless autoclave. Those rectangular chambers require reinforced corners, so extra steel, extra raw materials. The complexity inside means more electronics, more pipe work. There would definitely be a savings in the simplicity of design of a jacketed autoclave as well. And at end of life, a jacketless autoclave is almost entirely recyclable. It's kind of like a fancy big, like I said, Instapot. So there isn't much that can't just be recycled.
Thanks, Barbara. I do have another question. So, could you tell us a little bit about like the challenges for facilities or laboratories to adopt or upgrade to these technologies?
Yes. First of all, I love that you think it's an upgrade. Um, these kind of autoclaves that don't have a steam jacket are so much simpler and less fancy looking, but I also think of it as an upgrade. Um, the biggest challenge that we see is if you're in a laboratory that is sterilizing or processing a lot of media or liquid loads, jacketless autoclaves tend to take longer to cool. This is counterintuitive because there's so much less steel in a jacketless autoclave. They do cool more quickly overall. But in a jacketed autoclave, you can put cold water through that jacket to help cool the chamber. So it can be an adjustment for a place that processes a great deal of media because the cycle, instead of taking an hour and a half or 2 hours, may take 3 hours or 3.5 hours. That would be extreme, but that can happen. Most people find that the cost of a jacketless autoclave is quite a bit less than a fully jacketed autoclave. So if throughput is an issue, we see people buy two jacketless autoclaves if they're primarily processing media and need that kind of throughput. Trying to think if there are any other big issues for them. That is the biggest difference between them.
Thank you, Barbara. Is there any other question from the audience?
One more? Come on. in this in the world of autoclaves, the biggest complaint people have about autoclaves is that they break a lot, that they're out of service a lot. And that is another necessary evil of a jacketed autoclave. They're just highly complex. And sometimes when they're taken out of a medical setting where they're needed to run 24 hours a day into an on-demand setting, like a research setting, vacuum pumps can go out. There can be other issues just with turning them on and off, which wasn't the way they were built to be used. The simpler jacketless autoclaves tend to last. I think I just saw a question flash up from Vincent. They tend to last 20 years, maybe on the pressure vessel alone, and often longer. I don't know what the stated durability of a jacketed unit is, but I know that they come with a 1-year guarantee or warranty.
Thanks, Barbara. So Vincent is asking, what is the typical lifespan? Oh, so that's what you were talking
I think
about a little
so.
bit, right? Okay, you
I think-
addressed that.
Yeah, I think so. So we would say we would expect it to, as long as it's being maintained, we'd expect it to last for decades. I know the first one our company ever built in the 80s is still running in the Middle East.
Thanks for that. All right, unless no one else have a question, I think we will be ready to wrap up our session, probably a little bit earlier. It's the last chance to ask questions to Barbara. Thanks so much for being here today, Barbara. We truly appreciate you coming and showing us all this great information for us to consider. I would like to invite everyone here to our next webinar for November. It's going to be about the impact of global ESG regulations on corporate sustainability. This is going to be November 14th at 2 p.m. Eastern Time. We're going to have Aisling Anderson, Senior Project Consultant from Stantec. It's a global company focused on engineering, environmental projects, and all this good stuff. So please consider joining us. You will receive an invitation for this event in your email together with the presentation. So yeah, thanks so much for your participation today. Thank you, Barbara. Please don't forget to follow us on social media. Next slide, you already know us. We're on LinkedIn and Instagram. And yeah, thank you. And I hope everyone has a great rest of the week.
Thank you, Marley, and thank you for coming, everyone.
All right. Bye-bye. Thank you.
Bye-bye.